All right, welcome. Today we are diving deep into two words you hear thrown around all the time in computing, multithreading and multiprocessing. Now, I know they sound super technical, maybe a little intimidating, but the idea behind them is actually way more intuitive than you think. So let's get right into it.
So just stop and think about it for a second. Right now, you might have your web browser open, maybe some music playing in the background, a document you're typing in, all happening at the same time. How in the world does your computer juggle all of that without crashing? You can think of it like a single chef in a kitchen trying to cook an appetizer, a main course, and a dessert all at once. How do they pull it off without, burning everything? That's the core problem we're going to unpack. And here's how we're going to do it. First, we'll look at the challenge itself. Then we'll meet the two main contenders for solving it. After that, we'll put them in a head-to-head comparison, figure out when you'd use one versus the other, and wrap it all up with the single most important takeaway you need to remember. So that challenge, that kitchen problem, has a name. It's called concurrency. Just like our chef, a computer's processor needs a smart strategy to handle all these tasks efficiently. I mean, if it just did one thing at a time, completely finishing one before even starting the next, everything would feel painfully slow. We need a much smarter way to get things done. And that brings us to our two main strategies for solving this concurrency puzzle. A computer can use either multiprocessing or multithreading. Just think of them as two totally different solutions to our busy chef problem.
Okay, first up, multiprocessing. Sticking with our kitchen analogy, this is like deciding to solve the problem by hiring a whole new chef and giving them their own completely separate kitchen station. They get their own stove, their own cutting board, their own set of ingredients. The key thing here is they don't have to share a thing. You're basically just adding more independent workers to the job. And this approach has a huge advantage. It's incredibly reliable. Because each process is totally independent, think about it. If one chef completely messes up their dish, burns it to a crisp, it has zero effect on what the other chef is doing. The rest of the meal is safe. The system just keeps on running. This lets you break a massive job into truly parallel tasks, and if one part fails, it won't bring the whole thing crashing down. Now for our second contender, multi-threading. So instead of hiring a new chef, this is like training our original chef to become a master juggler. They learn how to chop vegetables while the soup is simmering, and then check on the roast in the oven while the sauce is reducing. All these little tasks, or threads, are happening within the same process. It's still just our one super efficient chef working in their one kitchen. The big win here is all about efficiency. Because all those threads are part of the same process, they share all the same resources. Our juggling chef doesn't need a second pantry or another stove. Everything they need is right there in the same kitchen. This saves a ton of memory and can give performance a serious boost. Okay, so we've got our two strategies. Hire more chefs and give them their own kitchens, or train one chef to be an expert juggler. Let's really put them side by side now and see how they actually stack up against each other. And this, right here, is the absolute most critical difference. It all comes down to memory. With multiprocessing, each process, each chef, gets its own private kitchen. No sharing allowed. With multi-threading, all the threads, all the tasks are happening in the same kitchen, sharing everything. If you remember one thing from this whole explainer, make it this. Now that difference in memory has a direct impact on cost and speed. Think about it. Setting up a whole new kitchen for a new chef, that's a new process, is slow and takes up a lot of resources. But teaching your existing chef a new juggling move, starting a new thread, that's incredibly fast and cheap. It's way more economical to create a thread than a whole new process. This table really spells it out, doesn't it? With multiprocessing, you're literally running multiple separate programs. So when the CPU switches tasks, it's jumping between entire kitchens. But with multithreading, it's just switching between different tasks within the same kitchen. And that's why creating a new thread is so much quicker. At the end of the day, multiprocessing can power through big jobs faster, but multithreading is often way more efficient with its resources. So that brings us to the big practical question. Which one do you choose? When do you hire a brand new chef, and when do you just train your current one to be a better juggler? Well, it all depends on the job you're trying to do. All right, let's make the case for multiprocessing first. When you need raw, unfiltered power and rock-solid stability, this is usually the way to go. You pick multiprocessing for jobs that can be easily split into independent chunks. Think of it like video encoding or complex scientific simulations. You can just throw multiple processors at the problem and let them all work in parallel. The code is often simpler to write, and like we said, if one process crashes, it doesn't take down the whole system with it.
Okay, now for the other side of the coin. Let's look at where multithreading really shines. This approach is all about responsiveness and efficient communication. Multithreading is your go-to for any task that involves a lot of, well, waiting, like waiting for a file to download or for a database to get back to you. While one thread is just sitting there waiting, another thread can be making sure your user interface doesn't freeze up. And because all the threads share the same memory, they can pass information back and forth super quickly. They're also incredibly fast to start and switch between. Of course, neither one is perfect, right? Multiprocessing uses a lot more memory, and getting those separate chefs in their separate kitchens to talk to each other can get really complicated. With multithreading, though, the code itself gets tricky. Since all the threads are sharing one kitchen, you have to be really careful they don't try to use the same salt shaker at the exact same time and mess up the whole recipe. That's a classic problem called a race condition, and it can be a nightmare to debug. So, after all that, after looking at the chefs and the kitchens and the juggling, what is the single most important thing to take away from all this? Let's boil it all down to one simple idea. Here it is. If you forget everything else, just remember this. Multiprocessing is multiple chefs in separate kitchens. Multithreading is one chef juggling multiple tasks in a shared kitchen. The entire difference, the whole shebang, comes down to that one concept: separate versus shared memory. It's really that simple.
And that leaves us with a pretty interesting question to think about. Our computers, our phones, everything, they're getting more and more processor cores every year. So does that mean the future is all about multiprocessing, giving every core its own separate kitchen to work in? Or will the lightweight efficiency of multithreading become even more critical to make the most of that power? It's a fundamental challenge that developers are wrestling with every single day. Something to chew on. Thanks for tuning in.